let's go ahead and get started here. Having a little bit of computer trouble, but we got some stuff we got to do first. So, not that you can, but don't use your computer while we're going through the non-CAD sections.
We don't get a choice. We don't get the choice.
Okay, so we're gonna start with these sheets. I was gonna pull some of this stuff up on the computer. We're gonna start with the engineering concepts thing. So the engineering concepts kind of just my catch-all topic, where I'm just gonna kind of throw a bunch of different things. We're gonna talk about different types of things. It's not always gonna be specifically engineering-y things, but it will be for a lot of them. So what we're going to go through here is we're going to talk about some different types of mechanisms. There's a few of these scattered throughout the class. So what we're going to talk about now is a few different types of drivetrains. Now, a lot of these mechanisms are, kind of tailored towards FRC, but you FTC students, it kind of applies to you guys too. So it's all pretty applicable. Okay, so a drivetrain is a type of mechanism that provides motion. And gives your robot the ability to move around the field. So there's obviously a lot of different types of these. It also provides basically the mounting structure that we attach all of our other mechanisms to. Now that's not necessarily required. Certain teams build their robots in such a way where, well, that's not really important, but the bottom line is we typically build the drivetrain as a separately contained unit, and it's self-contained and sitting there, and then we basically just bolt stuff on top of that. That's the way that most teams design their drivetrains. That's pretty common. There are some exceptions to that where it's kind of like their drivetrain isn't a separate entity, it's just kind of part of their robot. But so we'll talk about a few different types. There's a few different generic classes of drivetrains that are common in FRC. The most common is what's called a tank drivetrain. Now, basically, it's named that way because of the way it steers. So it has a set of wheels, occasionally tracks. A lot of people hear tank drive and they think tank tracks, but making tracks is kind of a difficult thing, so it's just not very common. You guys should have 7 pages total, just to count to make sure. 7 sheets of paper, I mean. So basically, most tank drivetrains have a row of wheels on the left side and a row of wheels on the right side. The first picture on your first page here, this guy here, this is a CAD rendering of our 2017 robot, two robots ago, and that's M54's drivetrain. That's a tank drivetrain. So basically, that had 6 wheels, 3 wheels on the right side, 3 wheels on the left side. To turn, we would drive one side of the drivetrain forward and the other side backwards or slower than the other side, and that would cause the drivetrain to turn. So it's kind of like a skid steer or a tank where you're driving 2 sides independently, and that's how you maneuver. They can be 4-wheeled, they can be 6-wheeled, they can be 8-wheeled. There's a lot of different types of wheels that you can use. We'll talk about different types of wheels in a later class because that's going to be a big, important part of the design process, is deciding what wheels in their drivetrain to use. They have a lot of advantages and disadvantages. So the how the drivetrain is physically constructed is pretty important. The frames are made in a lot of different ways, and that obviously you need to know how that works for when you're designing your drivetrain. So one common type, and the type that we've used so far, is we use sheet metal. Sheet metal is basically just thin, flat pieces of metal that are cut. We cut with a laser. A lot of teams use water jet, you can use a punch, you can do it with a drill press and a bandsaw if you have to. But you've got thin sheets of metal, you put it into a brake and you bend it. And the bending allows you to mount things at different angles, and it also gives you the strength of the bends add a lot of strength to design without adding any weight. You can have very thin material, but you can put bends in it, and that adds a lot of strength. There's another type that I have here on your sheets. This is the bottom picture. This is what's referred to in FRC as a West Coast drivetrain. And it's named that because there were several teams on the West Coast that kind of developed this years ago in First. This drivetrain's been around for a long time, but it was originally developed out by Team 254. You probably heard me talk about them, but them and a couple of other teams in that area were kind of the people who originally developed that style. But basically, it's made out of rectangular aluminum tubing. So instead of flat pieces of metal, they take tubing that's extruded. We'll talk a little bit more about some different kinds of raw materials and how you can actually buy aluminum, what kind of shapes. But basically, it's a rectangle. Actually, here's a piece. So this is square aluminum tubing. So it's tube, it's a square, it's made out of aluminum, pretty self-explanatory. They also come in rectangles. There's different wall thicknesses and different dimensions. So they basically are making their whole frame like that. You don't have to weld it, but typically it is welded. It works best if you weld it, just because there's not a lot of places to get brackets to bolt it together and stuff, but teams do it. Basically, the real idea behind the West Coast Drive is to, the main thing is to save space in the middle of the robot. So with the sheet metal frame.
Oh, now so now I have to do that.
With a sheet metal frame, you have a frame rail on one side, you've got wheels in between, and then you've got another frame rail, as you can see from the top picture on that first page. And so that eats up a lot of width. So you've got two, basically what people typically refer to as drive modules on the, you've got what's typically, so what the sheet metal frame looks something like this from the top, usually. You've got two, what we call drive rails. And then you've got a front and back pieces that kind of tie the whole thing together. And your wheels are in here. And basically, this area that's between these two drive modules is where a lot of your mechanisms go. That's where your electronics go. That's where your battery goes. So ideally, you want this space to be as big as possible and your drive modules to be as small as possible. Okay? So what West Coast drives do is they get rid of this drive rail. Okay? They move the wheels out, so the wheels are on the outside of your frame. And this drive rail moves out. Okay? Drive rail moves out. So that gets you more space, and then typically they drive with chains. There are West Coast belt drives, but typically there are chains. And the chains typically hug the inside of this tube, or are inside of the tube. So the idea is that you're saving space, and that it also saves a little bit of the weight, but there's also some reasons why you lose some weight savings as well. So a lot of people say West Coast drives are lighter. I contend that they're not. They're about the same, but they do save a lot of space. But you're sacrificing some structural rigidity because your shafts on your drivetrain are what we call cantilevered, which basically means they're like a car. Right? If you think of a car, there's not a bearing on the outside. There's a computer up here. You have a shaft and your wheels in the shaft. There's nothing on the outside of the wheel keeping the shaft from bending, right? That's how cars are. It's called a cantilevered axle. In FRC, your robot's driving over bumps, getting hit and stuff. It's pretty easy to bend a shaft. So West Coast drives don't offer a lot of protection against that, whereas a sheet metal type construction does. You've got a bearing on both sides of the shaft, so it adds a lot of support. So those are the two big types of tank drivetrains. I would venture to say, well, no, I'm not going to make that. I'm not going to make that venture. But there's a lot of them. There's a lot of different slight variations, but they're very, very common. I'm not going to say they're in the majority, or they're more than half, but they're very, very common. Okay, so that's one way of steering, so to speak. But there's another option. So if you go to your next page, there are drivetrains that are what we call holonomic or semi-holonomic. I'll get to that in a minute. It's not particularly important, but it's an interesting fact that I learned not too long ago. So, holonomic basically means that it can move in any direction at any time, right? So what it really amounts to is the robot can move sideways. So a tank drivetrain can drive forward and backwards, and it can turn, right? A holonomic drivetrain can drive forward and backwards, it can turn, it can also drive sideways. So it gives you a lot more maneuverability on the field, gives you a lot more ability to fit into tight places, and opens up some other options as well. By far, the most common, there's a few ways to accomplish this, and they're all kind of, you got to start making trade-offs when you want to do that. So by far the most common method is by using what's called a Mecanim Drive, which uses what are called Mecanim Wheels. So Mecanim Wheels they're wheels, and they have a bunch of rollers mounted at a 45-degree angle. So if your computers are up and logged in, are any of your computers not logged in? Okay, helpers, do you guys know the login?
No, there's ours is locked. It's locked.
Okay. If it's up and the keyboard works, let helper know to log you in. Okay, so
But my house just
Yeah, it's because he's taking control of our computers.
all right, so these are what Mecanim Wheels look like. Is that okay? Mecanim Wheels have a bunch of free spinning rollers around the outside of the wheel mounted at a 45-degree angle. And basically, if you take 4 of these on your drivetrain and you drive them each individually, by driving different wheels at different speeds, you can cause your robot to move sideways. Now, the big drawback that these have are traction. So when you're pushing against another robot, there's another robot in your way, you need to push them out of your way, or if you're trying to play defense and another robot can push through you, they don't have a lot of traction. Now, it's actually a common misconception that the reason that they don't have much traction is because when you're trying to push, that the rollers spin. That's actually not the case. The rollers actually, if you push against something, the rollers actually don't spin. But the reason they don't have much traction has to do with the fact that their tractive vector is at a 45-degree angle from your robot. So it's not, with a normal wheel, the vector that your traction works in is in line with the wheel. Whereas in this case, the vector that your traction works in is at a 45-degree. So you kind of lose, because of that angle, you kind of lose some forward tractive force. Either way, they're really simple to build. They're fairly easy to control. They are a little sticky. They're not very smooth. They're hard to make fast because you need a lot of torque to turn those wheels in opposite directions when you're trying to move to the side. But they're very, very common. You'll see a lot of them. The next thing is what's called an H drive. It's also called a slide drive. And effectively, it's similar to tank, where you've got wheels on the side of your robot like you normally would. You drive it like a tank. And then you also have is that computer next to you open, Dale? The one that Serena's sitting at? Yeah. There's a computer here, there's a computer down there, there's the computer right by Serena, and that's 3, so that should be good. Every seat's full, so you guys are just gonna have to plug in the holes. These are one farther down. Okay, so basically H drive is like a tank, right, where it's got wheels on the sides and you drive it like a tank drive, but it also has a set of wheels that are mounted perpendicular to the the other wheels. So if you look in your handout, you can see that there. Those wheels, these wheels are what we call Omni Wheels. And they're similar to Mecanim Wheels, where they have free spinning rollers, except right there by Dale.
There's not a chair there because Serena's sitting and
Oh.
I'm trying to pass a chair.
Oh, okay, all right. They're like Mecanim Wheels, where they have rollers around the outside, except the rollers aren't at an angle. They're perpendicular to the wheel. So if you put the wheel on the ground, the wheel can slide sideways, but it has traction in the forward when it's rolling forward, right? So you can drive around, you can drive forward, and you have traction in the forward direction, but they can free slide sideways. So by having wheels that are pointing forward and wheels that are pointing 90 degrees, you can drive them in different combinations to drive sideways and drive forward and backwards as well as turn. So H drive is probably the simplest, one of the simplest holonomic drives that's smooth. H drive is very, very smooth. With Mecanim, it's very, very sticky, so it's not very smooth. But H drive is very smooth, but it suffers from, it doesn't have any traction, right? Because there's always some direction that you can just push the drivetrain freely and give or take a little bit. They're very terrible for traction, but they're very, very maneuverable. And they're not that complicated to build. They do have a lot of extra motors because you have to have a whole set of motors devoted to driving your robot sideways, whereas like Mecanim, the motors that are driving your robot sideways are the same ones that are driving it forwards, right? So you're kind of like, the motors are serving multiple purposes on a Mecanim drivetrain, whereas on Slide, you have to have more motors that are each serving less purposes, which adds a lot of weight and complexity. There is also a version of, it's not a version of H drive, but it's kind of a similar concept. A lot of people call this drivetrain holonomic, although holonomic is actually a general term, and all of these drivetrains are holonomic to a certain extent. Basically, you take an Omni wheel and you mount it at a 45-degree angle on each corner of your robot, and you drive it similar to a Mecanim drivetrain where you drive each one at different speeds. And basically, because they're at angles and they're Omni wheels so they can slide sideways, you never get in a bind where the wheels are fighting each other. They all work together. That version is like pretty much the simplest and cheapest way to do holonomic drive there is, but it's typically not very functional because you've got to get all the speeds right because they're at 45-degree angles. So it's typically not very smooth. It's difficult to program, difficult to drive, but it is very easy to build and very cheap. One other thing I didn't mention, H drive has a really, really hard time on a non-flat surface. I don't know if you guys noticed, but there were robots this year that had slide drive, and as soon as they would get up on the platform, you know, that center module of wheels gets off the ground and they lose the ability to move sideways, right? So if they go up on a bump and one of their wheels goes up, it lifts that whole center module. It's not touching the ground anymore, and they can't move sideways anymore. And because that sideways module is the only thing stopping the robot from just free sliding sideways, because the Omni wheels, they can also slide sideways freely without any ability to stop themselves. So it's just, you want to run an H drive on a flat field because it just doesn't work on a flat field. Okay, and our last drivetrain here, which is technically semi-holonomic, which is not a well-defined term, but it's not, Swerve Drive is not actually what's called a true holonomic drivetrain, and I'll explain that in a minute. Swerve Drive has typically 4 independently rotating modules, so it has a wheel that can rotate on a swivel 360 degrees, and that wheel is driven. And it's got 4 of those. So each corner of the robot has a wheel that can turn independently and drive independently. And what that allows you to do is, using some creative programming, you can drive all of those, point them in different directions, drive all of them at the same time, and you get a really, really smooth holonomic motion, or semi-holonomic. You guys okay?
Yeah, I'm trying to figure out what the computer's
Okay. Is the mouse and keyboard working?
on. Yeah.
Okay.
It's the deep.
Okay, well then he's still working. Give it give it another 10 minutes or something. We got more stuff we're going to be doing, but give it another 10 minutes and go back up and get him if they're still not working. Okay, so Swerve, all right. So Swerve does not suffer from any traction issues because you have a traction wheel pointed in the direction you want to move at all times. So Swerve has very good traction. In some ways, Swerve actually has better traction than tank drivetrains because tank drivetrains often, in order to be able to turn smoothly, not all of their wheels are completely touching the ground at the same time. So they have kind of a weird weight distribution. Swerve, all 4 wheels are planted on the ground at all times, so they have very good traction. They can push and stuff quite easily. Swerve drives are obviously extremely complicated. There's a minimum of 8 motors to drive a Swerve drive. But they're extremely, extremely maneuverable. Now, technically, and I mentioned this before, technically they're semi-holonomic because technically they don't have the ability to move in any direction at any time. And the reason for that is you have to wait for the wheels to turn to face the correct direction before you can start moving in that direction. Now, in practice, they move very, very fast, so you can't really notice it. It is very slight, but it is there. It is a limitation. There are some designs called Castor Drive, which is basically the same thing as Swerve with a little twist that solves that problem, and we might see those emerging. I don't want to go into the details because it's kind of complicated, but yeah, so that's Swerve Drive. So at the beginning of the season, at the beginning of the build season, we're going to have a discussion where we're going to talk about what kind of a drivetrain we want. Now obviously the most common is a tank drivetrain. That's what we've always done in the past, but there are other options out there. We'll weigh the pros and cons, and if the game calls for something else, that's what we'll do. So drivetrains, just so you guys know, when you guys are done with this class, you'll have kind of the basic knowledge and the basic CAD skills to design a drivetrain if you want to. I haven't quite figured out exactly how our final project is going to work yet. I'll give you guys some more information on that in upcoming classes, but I would encourage you guys, it's a good project to take on before the build season starts, is to design your own drivetrain. Pick any kind you want and design it. There's a lot of resources out there, there's a lot of examples, there's a lot of CAD that you can download. I need the CAD handout, helpers. There's a lot of example CAD you can download, there's pictures you can look at. It's a very modular thing to work on, and they're fairly easy to design, but it's complicated enough that you'll be able to try out a few different skills and you'll be able to handle a fairly complicated assembly. Thanks, sir. Okay, so that's drivetrains. You guys have any questions? Okay. An extremely, extremely important part of the robot. So it's important that you guys understand how they work and kind of what's going on there. So that's drivetrains. All right, so we're going to talk about more off-the-shelf parts. I talked about what we were doing here last week, how we're going to go through a bunch of off-the-shelf parts, and so get you guys familiar with where we buy things, what different, what's a hex shaft versus a heat shaft. So this builds off of what we talked about last week with different kinds of shafts. Bearings are basically a mechanical piece that constrains 2 parts that move relative to each other only in the way that you want them to move relative to each other. So if I have a spinning shaft and I want it to spin in a particular place, I need to constrain it. I need to keep it from wandering all over the place. Right? I need to keep it from flexing. I need to keep it from bending. I need to keep it from going off at an angle. I need to constrain it and hold it in place while still allowing it to rotate. You can also, like for our elevator, right? It goes up and down. It's a linear motion. I have something that moves up and down. You have 2 pieces that are effectively sliding against each other. I need to make sure that it can't pop out, but still be able to move freely. So that's what bearings do. It's an extremely, extremely broad category of mechanical parts. We're going to just kind of touch on some of the basics, and we'll talk about the ones that we use most commonly. So the most simple kind of bearing is what's called a plain bearing, or you'll often hear them referred to as bushings. Typically, they're just a low friction material with a hole in it, right? And that's really all there is to it. It's you can see some examples there on your sheet. These here are bronze is a really common material that is used to make plain bearings or bushings. Because bronze in and of itself is fairly low friction and wear resistant. So when you have something, two parts rubbing up against each other, you obviously want, you don't want it to wear one part away. However, if one of those parts has to wear, which it does, you want your bearing to wear, because bearings are easier to replace than shafts. You don't want to damage your shaft, you want to damage your bearing, because bearings are easier to replace than shafts are. So bronze is soft, bronze is the part that wears, doesn't wear the shaft hardly at all. Bronze is also, in this particular case, what I've showed you here, all of these bearings are what's called sintered, which is a manufacturing method where they take a metal powder and they put it in a mold, and they basically they heat it up slightly and then just cram it down, right? So they can make all kinds of weird shapes. It's a very, very, very cheap manufacturing method. They can make millions of parts like that with sintering. But in this particular case, it has the added advantage of they can control how dense the material is. So if they want the material to be porous, they can make it porous, or they can make it nearly solid. They can't always get them completely solid. But in this case, they leave some pores, and then they impregnate the bronze with some sort of lubricating material. Typically, it's oil. Some bronze bushings also use graphite. They'll put graphite in there, which also is a lubricant. So bronze bushings, they're really cheap. They're really, really cheap. They're easily replaceable. They're really easy to design because they don't take a lot of space. You can get any size you want. There's some links there. We usually buy ours from McMaster-Carr because they have a great selection. There's also Aegis is a company. They focus solely on kind of high-tech plastic products. They have alternatives for bronze bushings that are in plastic, and they pretty much always have better performance than bronze does, because they're using very, very specially formulated plastics. That's like their specialty. They're a little harder to get. They're not quite as widespread, so availability is kind of low, and they're a little more expensive. But they take even less space. They weigh less, and they typically have longer life. Okay, so let's talk about a more common and more typical, what you may think of when you think of a bearing, is that's a ball bearing. Now I'm not talking about the round ball, because those are sometimes called ball bearings. Really, more correctly, they're called bearing balls, which is actually, to differentiate between that and a ball bearing. There's some pictures of ball bearings on the second page of your handout. I'm going to try to see if I can find a cross section here. Yeah. Okay, so the most common kind of bearing is called a radial ball bearing. A radial ball bearing has basically a few parts. It has an outer race. No, I don't want to do that. Go back. No, okay, it's not going to get any bigger. It has an outer race, which is this outer part, and it has a round groove cut on the inside of the outer race. These are precision ground, they're very, very precise. It has an inner race, and there's a round groove ground on the outside of the inner race. These the inner races put inside the outer races, and bearing balls are put around the outside that roll in between the two surfaces and provide support. And then they're held in place with what's called a ball cage, which is this kind of like stamped metal piece that kind of just holds the balls very, very loosely, but it keeps them from falling out, and it keeps them evenly spaced so the loads distribute. The groove, the round groove, keeps the ball. So if you think about pushing on the bearing in the forward direction, the thing doesn't just come flying apart, right? There's some engagement there, so that the bearing holds together, and it can handle load in this direction, and that's what's called the thrust direction. You're pushing against the bearing. The radial direction is you know, direction normally the bearing's supposed to support in, like side load on the shaft, but the thrust direction is pushing against it. Radial ball bearings don't fail under thrust load. Now there are bearings meant for handling thrust load, but you're not gonna pop your bearing apart if you put any load on that. Right? Okay, so they're very, very common. They're very cheap. Most bearings are radial ball bearings. Now there's a version of radial ball bearings. Radial ball bearings are typically have a round bore, which means you have to have a round shaft to use with the bearing. However, they do make, for the purposes of FRC, they make hex bore bearings. You guys remember that we talked last week about what hex shafts are and the fact that that's used pretty much only in FRC, but it's very, very common in FRC. Well, they have versions of radial ball bearings that have a hexagon hole in the middle instead of a round hole. That allows you to put a hex shaft through and support a hex shaft instead of a round shaft. And that's, we use a lot of hex bearings. Okay, so then, in addition to ball bearings, there are what we call roller bearings. And roller bearings, instead of using a sphere as the roller, they use a cylinder, or in some cases they use a cone. It's typically a cylinder though. And the cylinder has several advantages. There's a lot more surface area of the roller in contact with your shaft, right, which basically spreads the load out a lot more. So they typically have a lot higher load carrying capability. Roller bearings do over ball bearings or even plain bearings. They're less robust than ball bearings though in terms of their ability to handle like angular misalignment, like if the shaft's not aligned quite straight, it'll destroy roller bearings. Roller bearings also can't handle as high of speeds as ball bearings do. Well, due to a variety of factors, but friction is one of them because you have more contact there, they generate more heat. There are also other shapes of roller bearings. You can see on your next page here, there's what we call a thrust roller bearing. Thrust bearings, like I mentioned before, so these are, what we're talking about now are radial bearings. They're designed to handle load perpendicular to the axis of the shaft, right? So if you think of putting weight on the shaft, like the shafts that we use for axles on our wheels, you know, the robot's sitting on those, it's putting side load on the bearings, right? That's radial load. That's what most bearings are designed to handle. Well, sometimes you need to handle a load that's pushing and turning at the same time. If you'll remember the design of our intake that we used for Buckeye, used bearings that look exactly like this. They were thrust roller thrust bearings to handle a compressive load that was also turning. If you have, like I said before, radial ball bearings can handle a little bit of thrust load, but typically if you have a lot of thrust load, you really don't want to put them under that. Bearings they can handle a lot of load in the way that they're designed to handle it, but if you put them under conditions they weren't designed to handle, they break pretty much instantly. So they can handle what they can handle and they can't handle anything else. So it's pretty important to understand what bearings can handle what kind of loads and what you can subject them to without breaking them. And that's why we have thrust bearings, because if you need thrust load, you can handle thrust load. Now in it's not on your sheet, but in a lot of heavier duty equipment and more industrial applications and in cars, they use what's called a tapered roller bearing. And a tapered roller bearing is a kind of roller bearing, except instead of a cylindrical roller, they use a slightly conical roller, and it goes into a housing that is also conical. And so if you think about it, you put these together, you push on that bearing, right? It can handle radial load and thrust load at the same time. Then typically, with a tapered roller bearing, you have two of them in a set. You have two in a pair and you face them opposite directions so they can handle thrust load in either direction. That's what it's used in cars, because obviously when you're turning a corner and the car is, some centrifugal forces forcing you around a curve or something, you've got a lot of side load on your axle, so that you have to have something that can handle the side load. So tapered roller bearings are extremely, extremely strong. They're used in most industrial equipment and like vehicles and stuff. But they're typically larger bearings. They're pretty expensive, so they don't see a lot of use in FRC because they're overkill for most of our applications. But that's also this is actually a surprisingly common type of bearing as well. There's a lot of them in everything. Okay, so that's a few different types. And then there are linear bearings. So basically, you can take any of these types of bearings and you can kind of make a linear version that works in a straight line. Linear bearings are typically much more complex because linear motion's a much more difficult problem to solve because there's more degrees of freedom that you have to constrain to keep it from moving all over, to keep what you're trying to constrain from moving all over the place. Linear bearings are typically pretty expensive. They typically have to work with a special runner. It's a track and a bearing pair, and they have to work together. And they're typically pretty heavy and pretty expensive. So they don't see a lot of use inside FRC just because of that fact, but they're out there. In addition, at the bottom of your page, you can see what we call mounted bearings. Most kinds of bearings have some, you can buy them where they have a special bracket or they have a cast housing with bolt holes on it. So instead of having to drill a special hole and press the bearing into your own housing, you can just put a couple bolt holes, bolt the bearing to what you want to hold it, and go that route. Mounted bearings, they're typically made out of cast iron or cast steel or something, which is not a material that we try to use much in FRC. A, because it's not very impact resistant, and B, because it weighs a lot. So we don't use a lot of mounted bearings. We typically make our own mounts because we can make them lighter and smaller than you can buy them typically. But those are out there. Those are very, very common. You hardly ever see just simple radial ball bearings on industrial equipment because it's too complicated to machine your own housings. The companies that build that equipment typically buy mounted bearings. Okay, any questions on bearings? Did I go too fast? Did everybody get that? There's a lot of links in these documents. Well, not in the drivetrain ones. I put pictures in the drivetrain, but there's a lot of links in the COTS sheet. So if you guys want to go check out where we buy those from, you can get a sense for what's available, and do a little more looking on your own if you want to. Okay, so who is everybody logged in? Yes. Is anybody not logged in? Okay, does everybody have Inventor running? If you don't have Inventor running, get Inventor running. Okay, now, do you guys remember what we did first last week? You get a pass, Austin. You went to options. So you have your sheet in front of you, or you should. Go ahead and just go do those options again because these computers reset. So you'll have to do it every week. Did it?
Yeah, I think if you're signed into the Stellar thing, it saves it.
I have things that says big.
Well, it didn't save right up here. So if it saved it, great. If it didn't,
Wait, where do I go to?
and Michael and Coulter, if you guys be watching, if people need help. Okay, everybody get their settings changed yet?
Oh, I have the paper.
All right. As I said last week, I'm going to kind of add a little bit more detail to this. The handouts are really meant to just be a kind of a reminder, kind of a cheat sheet for you guys, and also a little bit of a kickstart, I guess, to the people who aren't here 1 week or another. They can kind of review the material. So I encourage you guys to take notes or whatever works best for you, so that you don't forget some of the stuff we're going to learn here, because not all of it's going to be in the handout. Okay, so I forgot to mention something last week, and I showed I think I showed one person or a couple people just who needed some help, and I went over it. But I meant to mention it last week, and I didn't. If you have a part, I'm going to just model something real quick. The whole power of Inventor is that when you model something, you can always go back and change what you modeled. You can always go back and edit. You can delete. You can change the part. You can make it fit. Because when you're designing something, you don't just design it and have it be done, right? You're always going to go back and do more stuff. So I made this cylinder. It's 2 inches in diameter and 3 inches long. Well, let's say I'm doing some prototyping or something, and I realize, oh, this part needs to be 3 1/4 inches long. Crap, now I've got to delete my part, create a new file, and model it all over from scratch, right? No. So you can always go back and change it. So I mentioned the browser and how important the browser was last week. This pane over here is the browser, if you guys remember. That's interesting. Okay, you just wrote a note. All right, so you can see here in the browser this part is listed, and everything under here is part of this part. Okay, you can see there's something called solid bodies, views, origin. We're going to get into this stuff a little bit later. But then you can see here's an extrusion. It's got a little arrow by it. If I click on the arrow, it expands, and you can see under the extrusion there's a sketch. This saves a history of everything that you're doing in your part. And when you need to change something, you can go over and find that sketch that you needed to change or that extrusion that you needed to change, and you can double click on it and edit that part. So I want to change the diameter to 1 3/4. Actually, let me back out of this and do this again so you can see. So I'm going to the sketch, double click on the sketch, that edits the sketch again. I can double click on my dimensions or whatever, change dimensions, click OK, finish the sketch. You can see my part got smaller. If I want to change the length of the extrusion, I can double click on the extrusion, change the length, 3.25, click OK. The length of my part changes. So I don't know when you guys are messing with it at home if you guys figure that out or not, but that's how that works, and that's really where Inventor starts to be more powerful than like Maya or something that's like a 3D graphics type of modeling system as opposed to a CAD system. That's really the key difference there. Okay, so you guys all got that? Okay, so now we're actually gonna launch into some new stuff. That's important as we move forward in the class. You guys are gonna have to get used to going through and changing things as you go, because we're not gonna always model things and leave them the way they are from the beginning. Okay, so we're gonna talk about we're gonna go back to sketches. We're gonna go to some more 3D modeling a little later tonight, but we gotta flesh out our sketching skills before we can do that. So create a new part, and it should come up with a sketch if you guys change your settings. Now you can see here up on my screen, you can see here this kind of grid of little buttons that all have little icons on them. These are all constraints. Now I mentioned last week that we were going to create something called a dimension constraint, and that basically was how we were saying, here's how big our circles are, here's how big our rectangles are, you know. That's a dimension constraint. Okay, well, the dimension constraint is only one of many different kinds of constraints that we're going to use. Now, dimension constraint is the one you're probably going to use the most, but there are other types you're going to use very, very frequently. So I have a list and kind of a semi-decent description of what each of these constraints do. The big one is like coincident, which is a little bit of a weird one to understand just because it kind of runs under the radar most of the time. But if you think of a line has 2 points, right? One at each end of the line. And more technically, I should call it a line segment, but in Inventor, it's a line. So a line has 2 points, an end point on each end, right? You don't really see them, but if I create a line, you know, when I'm clicking and making a line, I'm clicking where I want the endpoints to be. And then you can go back and you can hover over and you see this little like red dot shows up if I'm hovering over the endpoints. There is also a midpoint in lines too that you can snap other geometry. Like if I want to create another line, I can hover over the midpoint. You see I get this green dot. Okay, and if I hover over the endpoint, I get this green dot. Otherwise, I just have a yellow dot. If I get a green dot, I can attach. That attachment, when I talk about attaching something, that's actually automatically creating a coincident constraint. Okay. Now we'll get a little bit more into automatic creation of constraints here in a second, but that's coincident constraint. They're everywhere. Your whole sketches are going to be put together with coincident constraints. A lot of them you're not going to have to do manually, but some of them you will. Okay, so then there's I'm going to run through these real quick. You've got a collinear constraint, which is this one here. And if you hover over these, a tooltip shows up, and they actually, most of them have a graphic that shows you how to use them. So they're very, very user friendly. A collinear constraint makes two lines line up, make them collinear, makes them in the same line. That's useful in a lot of cases. This is a concentric constraint, which basically takes, for circles and arcs, it makes them have the same center point. So they're concentric. I'm not sure how else to say that. They have the same center point. The arcs and the circles might be different diameters or radiuses, but they'll start at the same center point. They'll be kind of inside. They'll be kind of inside of each other. This is fixed. And I want to tell you right now, I've been doing CAD for 8 years, and there has never been a case where I needed to use fix. There are plenty of cases where I could have used fix. There are no places where I needed to use fix. So you guys should never use fix. Don't use fix. It can cause a lot of problems. So there's basically no situation where you should use fix. We're not going to use it in the class at all. This constraint here, this is a parallel constraint, makes two lines parallel, obviously. This one's perpendicular, makes two lines perpendicular. The horizontal constraint and the vertical constraint, if I, like for instance, this line here, it's an angle, right? I can click the horizontal constraint and then click on the line, and it makes the line horizontal. And then the line will stay horizontal. No matter what else I do in the sketch, that line's going to stay horizontal. Constraints are like logical rules that Inventor keeps track of all the constraints that you apply, and your sketch has to obey all of those constraints. So you're kind of giving it conditions. So you can be any shape you want, except this line always has to be horizontal. Oh, and that line has to be attached to that line. And these two things need to be this far apart, right? You're kind of creating a list of rules, and then Inventor's going to figure out a way to make all that geometry fit, right? Which is why when we're working on a lot more complicated sketches, you'll change a dimension over here, and other stuff in the sketch will change, because it's, Inventor's updating it to fit it to your set of rules that you've specified for the geometry in that sketch. Okay, so I'm going to undo this. I can also do a vertical constraint, which obviously does the opposite, makes things vertical. Now this has another use too. So if I have like two circles, say, right, and they're different places, and I want them to be in line horizontally, I can click the horizontal constraint, click the center point, and click the center point of the other one, and now they're lined up horizontally. And I can do the same thing vertically as well. I'm sure you guys can imagine how that works. Okay, so that's how horizontal and vertical work. They're pretty versatile. Typically, well, we'll go to that in a minute. Tangent. Tangent is a little bit of a more abstract concept. Basically, tangent is where you have a circle, or you have an arc, and you have a line touching that arc, or a line or another circle, touching that line at one and only one point. So for instance, this line like this line is not tangent, okay, because it's touching the circle at 2 points. This line is also not tangent to this circle, because it's touching it. If you had extended the line out, it would also touch at 2 points. This line here is not tangent because it's not touching the circle at all. Okay, so tangent is where it's touching like that, right? One and only 1 point. So the tangent constraint allows you to make a line tangent to a circle. And you'll notice I can still slide the line back and forth, right? But it's stayed touching the circle. Okay? Now it also works for two circles. Pretty much anything you can do to a circle, you can also do to an arc. So I'm kind of just generalizing when I say circle, but it also applies to arcs. Arcs are just sections of circles, right? So you can make two circles tangent, right? And then they touch at one and only 1 point. This is very useful. You're going to use tangent constraint a lot because we typically don't do a lot of sharp corners because A, they're sharp, and B, especially if they're interior sharp corners, they can cause what's called stress risers, which basically it focuses the strength and your metal is more likely to crack or tear at a sharp corner. So we try to round a lot of our parts off because it makes them look nicer and it makes them stronger. Okay, so then this here is smooth. This applies to splines. We're not going to get into that in the class. I don't think I've ever used that constraint. This is a a symmetric constraint, which basically if you have a part that's symmetrical, it can help you make the part symmetrical so you don't have to repeat constraints on either side. I use it a lot. You don't have to use it. In a lot of cases, it's just more convenient to use it. I'm not really going to go into exactly how that works, but if you guys want to mess around with it, use it, be my guest. It's quite useful. And then this here is equals. This is also a very useful one, but it's kind of pretty simple. Basically, if I have two lines, right, there's a short line, there's a long line, okay? I want them to be the same length, right? I can click equals, click on one line, click on the other line. Now these two lines, no matter which direction they're facing, they're always going to be the same length. All right, the same thing applies to circles. If I click the equal sign, click on one circle, click on the other circle, oops, click on one circle and click on the other circle, the two circles are the same size. So now if I make a dimension here and I dimension this circle and I say, hey, I want this thing to be 4 inches, right, the other circle will change sizes. Right, then if I change this and go 3.5, right, the circles change sizes. And because these lines are unconstrained, they're kind of floating around, and Inventor's doing stuff with those as well, but that's just because they're not constrained. So, but yeah, so you can see how by adding constraints, you can align geometry in such a way that it's attached to each other and it acts the way you want it to act without having to add a whole bunch of dimensions or trying to slowly drag stuff on the screen and make it work. Okay, so by default, Inventor places a few constraints automatically just by when you're clicking and placing lines or placing circles, it will create some things automatically. When you're creating lines, you can see here if I click and I keep it to the side, you see this little symbol right here? This little symbol means that it's going to automatically place a horizontal constraint on that line because the line is horizontal when I'm placing it. Same thing with vertical, okay? So you see when I place the line, right, it shows the little symbol saying it actually did add a vertical constraint. And if I do this, now this is saying it's placing a perpendicular constraint between these two lines because they're perpendicular. Okay? If I click again, it shows me that it did place a perpendicular constraint. Then if I go vertical, place another perpendicular constraint, and so on and so forth. So vertical, horizontal, and vertical, it places those automatically. It places parallel and perpendicular automatically. It will also place well, obviously it places coincident constraints. This corner, right, these two lines are joined by a coincident constraint. So if I take a line, right, I take two separate lines that aren't attached, and I want those to attach. So I want these two lines to attach. I can click the coincident constraint. I can click one endpoint. I can click the other endpoint, and you see they snap together. Now they're attached, so no matter what I do, I drag these lines around, they'll change size in the same position, but they'll stay attached to each other. That's important. If you want geometry to attach to each other, you've got to attach it. You can't just put it close, right? It's got to be actually attached. Okay, is that making sense to you guys? You guys get where we're going with constraints? Okay, all of them there's a lot of them. All of them are pretty simple. When you guys are on your own time, play around with them, you'll get the hang of it. There's really not a lot to it. Once you get a lot of constraints in a sketch, it can be a little bit complicated, and it can do some things you wouldn't expect because you have constraints where you don't think you do. Remembering that Inventor automatically places a lot of constraints on its own is important because sometimes Inventor will place constraints that you don't want it to place. So that goes into our next topic where we're going to talk about, we talked about how to add constraints. Are you guys all comfortable in adding constraints? You think you can select the one you want, click on one thing, click on the other thing, and have them snap to each other? Okay. So now we're going to talk about how to remove them. Because like for instance, let's say I created this part here, right? Actually, one quick thing before I do that. Coincident constraints, you can also place coincident constraints another way by typically just clicking and dragging. So like I talked last week about how your parts always need to be what we call fully constrained. So if I made this part, right, let's say it's a triangle. Let me make a triangle here. Okay. I can dimension this triangle. Okay. Right, this triangle is fully constrained, right? This triangle can't change shape, it can't change size, but I can still click and drag it around. I can still move this triangle around, which is bad. I shouldn't be able to do that. So I need to attach it. I need to attach it to the origin point somehow, so that it stays in place. That's important. So to place a coincident, you can place a coincident constraint by like just picking a corner and attaching the corner to the origin point. That works. You could use dimensions to attach it to the origin point and just say I wanted an inch away from the origin point, right? You could do that too. But a real easy way to do it is just click and drag a point and snap it to another point, and it'll automatically place a coincident constraint for you. You know, so if you have, going back to what I was talking about before, where you've got two lines, I can just click and drag one line, snap it to the other. You'll notice you get this little, you get that little green dot. That little green dot is telling you it's going to automatically place a coincident constraint there. So now these two lines are attached. So coincident constraints can often be placed just by clicking and dragging and snapping one thing to another thing, right? Okay, so let's.
Where do you find that? The coincidence constraint?
It's this one right here.
Okay.
Little corner.
Okay.
Yeah. And if you hover over those, it'll tell you what they are.
Okay.
Okay, so let's talk about how to delete constraints. So let's say I made this little triangle, right? I don't want this triangle to be a right triangle. I want it to be some other angle. And Inventor automatically placed a perpendicular constraint, so now, you know, I'm out of luck. So we want to delete the constraints. So deleting coincident constraints is slightly more complicated. So for what I'm about to show you applies for anything that's not a coincident constraint. We'll talk about how to delete coincident constraints here in a second. So basically, if you press F8 on your keyboard, it'll show little icons everywhere there's a constraint. Now this sketch is not very complicated. You guys can put some lines on your screen if you don't have any, or you can watch me. I don't care. You can see here's a vertical constraint, and you can see here's a perpendicular constraint. Now, what I want to do is I want this line to be horizontal, and I want this line to be at some other weird angle. So I need to delete both the perpendicular constraint and the vertical constraint because I don't want either of those. So it's a little bit finicky. It can be kind of a pain in the butt to delete constraints. But hover over the constraints with your mouse, and you have to left click first, and then don't move your mouse, and then right click. Okay? You've got to left click first, then right click, and that's in your handout. If you guys forget how to do it, it's in there. But left click on the icon, then right click without moving your mouse. Then you can go up and hit delete, and it'll delete the constraint. So now you can see, that. Well, I gotta hide the constraint. So like for instance, I can't click and drag on stuff right now because it wants to grab like corners and stuff. Want to grab other things. So you can press F9 to hide the constraints again. You can see now this line isn't vertical anymore, but it's still perpendicular, and I don't want it to be perpendicular. I want this line to be horizontal and this line to be at a weird angle. So I press F8 again to show your constraints. Left click on the constraint I want to delete, right click and hit delete. Okay, so now there's no constraints. F9 to hide it again. Now I can move both these corners independently without it pulling other things with it. Now, I said before that I want this to be horizontal, so what am I going to do? What is the sequence of...
The horizontal constraint.
Yeah, how would I do that? How would I apply a horizontal constraint to that line?
Oh. You click the horizontal constraint. And then click the one you want to
then
do.
click the line. So go up, click horizontal, then click the line. Okay. Now I didn't do anything to this other line. This other line can still move around, but now this line is where I want it to be. Now we didn't talk about it last week, but the dimension tool can be used to create angular dimensions as well as linear dimensions. So if I have two lines that are not parallel, and I click the dimension tool, I click one line and I click the other line, it'll create an angle dimension in degrees, so that I can tell it, 120 degrees or something, right? So you can use the dimension tool that way as well. All right, how do you guys feel about constraints? You guys get the hang of it? Okay, so let me see. So let me show you one other thing. I'm gonna have you do a little exercise before we move on. This is important. This is the only time I'm gonna go over constraints. And like in a couple weeks, we're gonna be doing some fairly complicated sketches with a lot of geometry and stuff. It's important that you guys understand how constraints work and get that going. So if you guys have a computer at home, you can practice putting together some sketches. Make all kinds of weird shapes, whatever you want. You don't even have to extrude it. Just make some sketches and play with some dimensions, play with some constraints, delete constraints. Oh, speaking of deleting constraints, I was going to tell you guys how to delete coincident constraints. Okay, now a rectangle, for instance, there's nothing special about a rectangle. A rectangle is just four lines that automatically have coincident constraints attached to them, right? That's all a rectangle is. So I can make a rectangle here, and then let's say I want to do something weird on this corner, and I don't want these two lines to be attached to each other anymore. I can press F8. Now you'll notice there are no symbols that show coincident constraints here. There's nothing there. Well, where do I go? Okay. So what I do is I hover over these like yellow squares at the corners, and you'll see a couple icons appear. Now for instance, there's going to be an icon for each piece of geometry that's involved in a constraint. So for instance, this symbol and this symbol here, these two parallel constraints, these two lines that are parallel, these are both the same constraint. Okay, so if I hover over one line, you can see they both highlight, both lines highlight, and both constraints highlight. Right, so if I delete one of these, I delete the other one. Okay, so the icons show up in pairs. There's always two icons. So if I hover over this corner, you can see there's two icons, but it's actually, each one of those icons applies, it's the same constraint. Right, those two icons are the same constraint because it's one corner, two lines on one corner. So you can just do the same thing, hover over the line, then hover over, you can see which line they each belong to. They both show up. So you can hover over the one you want to delete, left click, right click, just like we did before, and click delete. And because I deleted that horizontal constraint before, now I can move this line around and it's not attached to this corner anymore. So now if I wanted to, I could pick a different line. I could turn this into a completely different shape if I wanted. Hide my constraints, right? Make a little house shape, whatever I want to do, right? So when you're going in, if you're editing a part that's already been modeled and you need to do something crazy where you need to add some geometry to it, or if you want to start with a basic shape and then kind of change the basic shape to make a more complicated shape, you can do stuff like that where you can throw a rectangle in there and you can take the rectangle apart, so to speak, by deleting coincident constraints, deleting horizontal constraints and such. So that's something you can do. You can, now, in a lot of cases, like for me, parallel and perpendicular constraints, I don't like it that Inventor applies those automatically. When I'm working, I typically don't want Inventor to place perpendicular and parallel constraints for me. Vertical and horizontal is fine. Parallel and perpendicular I don't really like so much. You can select which constraints Inventor is allowed to place automatically. There's instructions. We're not going to change it, and we're going to keep the settings default just because I don't want you guys to have to go through and change a ton of settings every week. And for what we're doing, it's not going to slow you down if it does. Plus, I'd like you guys to have some practice. If it places a constraint that you don't want it to, I want you guys to have some practice deleting, going in and deleting it, and understanding how to find constraints that you didn't think were there. But anyways, if you guys want to change those settings, there's instructions in your handout of how to do that. Okay, so I'm gonna give you guys a shape here, and I want to see if you guys can do it. I'm gonna give you. You're gonna need one piece of information that I haven't given you yet. Once you guys kind of get well, I want you guys to make this shape, and I want this to be the origin. I want you to attach this corner to the origin, and go ahead and put a smaller circle in. You can make the dimensions whatever you want, but go ahead and make that shape.
The one on the right side.
Yeah, not the drivetrain.
And we are talking about just a 2D sketch. with
Just a sketch, yeah.
constraints, right?
Don't extrude it yet.
Get roasted.
Oh, that's not what I meant to erase. Gosh darn it. I wasn't happy with my erase.
Circle. Alright, that's not correct.
That's a nice circle.
You're a bad person. I'm like a great person. So, I did it.
Did it? All right, you guys about done?
It took me like 10 minutes to figure out how to get on it while you were doing all that stuff. I was like, what?
Oh right, yeah, you weren't here last week, so.
You're weird.
We actually make a lot of parts. This is actually a fairly common shape. We actually make a lot of parts that look like this. Because you use it, you mount it at the bottom, and you put a bearing at the top. Okay, so I made a little mistake here on my screen on purpose to show you guys something that can happen when you're dealing with tangents. Okay, and notice on this side here, I've got this line, and this line is tangent to the circle. Do you guys do the same thing?
Sure.
You guys make a tangent? Okay. So you'll notice there's an endpoint. If I get in here and I kind of hunt around for it, I can get the little dot to show up. And that's the endpoint. And I can click and drag and oh, it doesn't move. That's a good thing, right? I don't want it to move. Well, if I go over to the other side, I can find the little dot, but I can move it, right? I can move it up here. Now my line's here. I can click and drag. I can move it down here. It's tangent to the circle, but not attached to the circle, okay? So this is something that you'll see. You can do it accidentally pretty easily. You know, beginners do it a lot. They don't realize necessarily that putting a tangent doesn't actually attach the line to the circle. So in order to do that, you need to place a coincident constraint between the endpoint of that line and the circle. Now, how would I do that? There's a couple different ways I can do it. How could I do that?
Click on the line and hit the little circle on the end of it, and then drag it and attach it to the circle, on the circle, you know, the little,
Mine says it already exists.
oh, snaps is what I'm thinking.
Right, yeah.
Snap it.
Yeah, so I can click and drag on the endpoint of the line and just snap it to the circle, like so. Click and drag and snap. Right, now I got a coincident constraint, now it doesn't move, right? That's easy. Why is it not? Undo it. There we go. The other thing I can do is I can go up and click the coincident constraint, click the endpoint of the line, click the circle. right? Now, typically dragging and dropping it is faster, but in some really complicated sketches, it can be very, very difficult to drag something and have it actually snap to what you want it to attach to. So for complicated sketches, I typically do the second method, where I'm just click the constraint and click what I want to attach to each other. For simpler sketches, just click and drag, it's faster. Okay, so is everybody got that? Everybody clear? Okay, do you guys think you can go home and do some constraints and kind of get the hang of it? Okay, so now we're going to do one other thing. This here, we don't really want it to look like this, right? We've got an extra piece of line that we don't want. That's this. We want to get rid of this. We want it to look like that, right? 'Cause we could make that could be a bracket. We could laser cut that. We could put a bearing here in the middle. We could put some bolt holes down here. Okay, so this is what we want it to look like. So there's some other tools that I haven't gone over in the sketch environment that I want you guys to explore on your own this week. I kind of pointed out what a few of them are in the handout. And I'm going to just run through a couple of them here real quick just so you guys can see what's possible. There is what's called a trim tool. It's up here. Okay, so if you click the trim tool, basically the trim tool removes pieces of lines and shapes that are between other things, right? So I can click here and I could remove, you can see how this hovers over, it's a dotted line, I could remove that piece and it kind of cuts the top off but leaves the bottom part of the circle. I'm going to undo that. But what I want to do is I want to click the trim tool and click the bottom half and it trims the bottom off. Now you'll notice all your dimensions, all your constraints, everything stays, but it just neatly cuts off geometry that you don't want. Now, that's useful in a lot of cases because sometimes you'll end up with a lot of extra geometry. You want to trim it out. Just be aware if you trim too much, you'll end up removing some constraints, and you'll have to go back in and add some constraints to get your geometry to fully constrain again. But that's the trim tool. That's pretty easy. Now let's say, what did I say before? I said, well, often we don't like sharp corners, right? We want round corners, right? Because round corners, they don't stab your finger and they don't do bad things. So there's what we call a fillet tool. Now this is not fillet. It's spelled like fillet. It's not pronounced fillet. This is a completely different word. It's pronounced fillet. If you call it fillet, people will probably laugh at you. And if they know what they're talking about. If they don't know what they're talking about, they might join you. This is not a GIF situation. Okay, so fillet basically takes a sharp corner and automatically rounds it. It places a little arc there in the corner of a specified radius, and it attaches to geometry automatically. So if I click the fillet tool, I get this little box that pops up, and I can type in a diameter. I want a 1/4 inch, which is 0.25 inches. And then I can click on one line, and I can click on the other line, and you can see the little green, when I hover over it, it shows me the little green highlight. I can fillet this corner, I can fillet this corner. So I can click the other line, bam, makes a little fillet. If I want to fillet on the other corner, it's I can click this line and click this line, and it makes another fillet. Then I can just hit escape when I'm done. Right, and then it automatically places this little dimension that specifies the size. So if I want to make these bigger, like a 1/2 inch, I can double click on the dimension, edit the dimension. Right, now I have bigger fillets. I can make even bigger if I want to. I can make them 1-inch fillets. Right, round the whole bottom of the part off. Okay, I can always go back and change them. Now you'll notice I'm changing one dimension. I'm changing one dimension, and the other fillet is changing size. Now, if you hit F8 on your keyboard, you'll notice there's a little equal sign. When you're doing fillets and you do a bunch of fillets all in one go, Inventor will automatically place equals constraints between all of those arcs, which will make all those arcs the same size. So if for some reason you create a bunch of constraints and then you realize, oh, I don't want all of those to be the same size, I want to change just this one, you can go in, you can edit, you can delete the equals constraints out of there, and then you can attach a dimension to it. So like, let's do that real quick. So I can go in, delete the equals constraints. Now you'll see this line over here, I'm gonna hide my constraints again. This line turns purple, right? Which means it's now not constrained. It can change size at will. So now I can just click a dimension, drop a dimension down, click on the arc, place the dimension down, and make this a 1/2 inch radius if I want to. When you dimension circles, by default, it does a diameter. But when you do arcs, it does a radius. Just keep that in mind. You can change that, I think you can change that. But that's typically what you want. You typically want arcs to be a radius dimension. So now, I created those two constraints, deleted it. There's one other thing that's extremely powerful in Inventor. Well, there's two things actually. We're gonna go over these very briefly and then move on. All right, if you go into the edit constraint dialog, you can do math in these. You can just type in equations in these boxes and Inventor will figure it out. And when I say that it can, do it, use it. Don't sit there with a calculator calculating what dimensions you need when you can just type the calculation in the box. So let's say I want 3/16 of an inch, right? Well, I don't know what that is in decimal, so I can just do 3 divided by 16, right? 0.188. It's actually 0.1875, but that's fine. Everything in this window rounds to 3 decimal places, but you can do things that are more decimal places, and you can actually change how many decimal places that rounds to, but it gets cluttered. So you can edit a dimension. You can type in. I could do 0.5 minus 0.25, right? I can do whatever I want. I can do 36 divided by 3.1415 minus 20. It ends up being a negative number, but you get the picture. So you can type equations. Now there's one other extremely powerful thing you can do. You can make dimensions use other dimensions in their equations. So let's say that I want this fillet, this little fillet, to always be half the size of this fillet, right? And I don't want to have to manually go in and change the dimensions every time. So what I can do is I can double click on the dimension. You can see here, you see how this is highlighted? So if I just start typing, it'll replace whatever text is in that box. If I click on another dimension, you see how it says D9 in here? Every dimension has a name. It's D and then a number. You can see I'm editing dimension D8 right now. So you can, anywhere you type D8, it's going to take the value of that dimension and insert it. If you guys are familiar with programming, you guys know what variables are. This is a variable. If you don't know what that is, don't worry about it. You can click on a dimension and it'll place that dimension's name inside, and basically where Inventor sees D9, it's going to put half an inch. But if I change half an inch to 3/4 of an inch, D9 is going to become 3/4 of an inch. So what I want to do is I want half of D9. That's the dimension I want. So I can take D9 divided by 2, press enter, right? Nothing changes, right? Because it was already half the size. But if I go over here and I change this dimension to 0.75, this dimension over here will change as well. That's an extremely, extremely powerful part of Inventor. You can do all kinds of crazy math. When you're doing really complicated things, that is extremely useful. So you get used to doing that. If you have 30 holes, well, it's kind of a bad example. If you have 30 holes and you want them all to be, or 30 circles and you want them all to be the same size, use the equals constraint. But you could dimension each one and set all the dimensions to be equal to each other. Okay, so that's extremely powerful. There's some other stuff. There's an offset tool which basically does this, where it'll create you can just click offset. It'll create an offset copy of whatever you click on. Basically, there's split. There's rectangular patterns where if I want a repeating piece of geometry, I can do that. I encourage you guys, mess with some of these tools up here, figure out what they do. There's all kinds of stuff on YouTube if you get lost. Most of the stuff, if you hover over it and you just wait a second, it'll pop up this whole big box and it'll tell you exactly what it does. Some of them even have a little video that shows you, I'm not sure if this one does. Some of them have a little video that'll play that'll show you how to use a little animation. So that's kind of the basics of sketching and some of the not so basics. Those are all the basic tools that you need to make pretty much any sketch you want. We'll touch up a little bit more. I'll show you, like, there's like one other thing I want to show you, but I'm not going to get into it tonight because we don't need it yet. So, now this part here, do you guys have did you guys model this? You guys follow along at all? Well, you guys have whatever you have on your screen. Okay, so you guys have a circle and some outer profile. I want to show you something that we kind of hinted at last week, but didn't really get into a whole lot. Finish the sketch and click the Extrude Tool. Okay. Now you'll notice before, I'm gonna create a new part here real quick just to show you the difference. Right, if I just have a circle like we were doing last week, 2 inches in diameter, I hit the Extrude Tool, right? I hit the Extrude Tool and you see immediately it starts showing me 3D geometry, right? Okay, well if I do that over here, click the Extrude Tool, you'll notice no 3D geometry. Well, the reason for that is when you're creating a sketch, you're creating what are called profiles. Okay, each profile is highlighted in green. So this is a profile. A profile is basically a closed loop. It has to be closed. You can't have a U shape made out of lines. That's not a profile. Those are just lines, right? But if I close it and I make it a closed shape, that's what's called a profile. Okay. In a sketch, you're creating a bunch of profiles, and basically each profile is going to border one or more regions. Okay? So like inside of this circle is a profile, right? Inside of the circle, that's a region. Okay? Inside of this outer loop here, this is a profile, right? Between the circle and this outer profile, that's another region. So when you click the Extrude Tool, you can hover over and it'll highlight the regions. Okay? And you need to specify which regions you want to extrude. So if I want to just extrude this region, right? I click on it, all of a sudden, hey look, there's my 3D preview. Okay? Well, if I want to extrude both of those, I can click on the inside one too, and it'll kind of add it, right? You're basically keeping track of a list, behind the scenes, keeping track of a list of what regions that you want to extrude. Well, let's say I clicked on one by accident. Ah, crap. I didn't want to extrude that middle part. I wanted that to be a hole. Hold the control key down, and then you can see now I can hover over them again and click on the one you didn't mean to, and it'll remove it from the extrusion then as well. Okay? So I can sit here and hold control and take it away and add this one to the extrusion, and now I don't want that, hold control and click that one. So play with that a little bit, get used to how that works. Okay, and then okay, so next, I'm gonna try to get done a little early, and then I'm gonna give you guys just some parts I want you to model and see if you guys can do it. But we got a couple more things we're gonna cover before we do that. Okay, so this is all well and good. We can do a lot, right? I mean, this is a fairly complicated part. I mean, this is no cylinder, right? This is a potentially useful shape. Okay, we could, using what we know, go in and add more shapes, right? I can add a circle, right? I can dimension that circle to the edge of this part, right? I want it 1 inch, maybe 1/2 inch off the bottom. It'll let me place the dimension. There we go, 1/2 inch off the bottom. Make it, 1/2 inch in diameter. And I can extrude this, right? Make a little pin, right, or something, right? You can keep adding onto your parts, okay? But sometimes you want to remove material from a part. I'm going to go over here to my cylinder. Go ahead and model a cylinder like this real quick.
add a part and switch between them?
You just go up here and click this button here, and it'll bring up this window, and then you just double click on standard.ipt.
And how do you get back to the other ones?
They're down at the bottom, there's the little tabs. So you can just click the tabs back and forth. Yep. You can have, I mean, it's, if you fill up this bar, that'll just add a little scroll bar and
Okay.
keep going, so you can have 100 parts open if you want. Yep. Okay, everybody have a, everybody have a cylinder? Okay, so sometimes you want to cut. Sometimes you want to take material away from a part rather than adding to it. Okay, so let's create a sketch on the end of this cylinder. You guys remember how to do that, right? Click sketch, click the face that you want the sketch to go on. If there's something that I go too fast and there's something you want me to repeat, just say so. Say the word. I don't want you guys to get lost. I want you guys to be able to do what you need to do. Okay, so we've got a sketch on the end of this. Create a circle that's smaller than the bigger circle, however big you made it. I'm gonna make mine 1 inch, and then finish the sketch. So you guys should have what I have on my screen, right? Okay. So now activate the Extrude Tool, and you'll notice, you know, here, because we just like we were talking about before, we just have one profile, which makes one region, right? So that's Inventor knows that that's the region that you want to extrude. Okay, but we don't want to extrude out. We want to cut in. So these buttons here, this here says join. This is what's selected by default. The button below it says cut. And there's also intersection, which is I've never used ever, not once. It's kind of useful, but in certain cases I just never needed to use it. So you can click cut, and you'll see the little arrow flips direction. This part turns red, and it starts showing you that it's going to cut material. Okay. Now I can set my depth. Now it just happens that I extruded it 2 inches long. It remembers the last number you typed in there, so it's just I extruded it 2 inches long, and it's wanting to cut 2 inches deep, so it's going all the way through the part, which might be fine if that's what you want, but I just want it like 1.5 inches, right? Okay, so it's not going, so I kind of make it like a little, you can finish the sketch, I kind of make it like a little cut, right? That might be useful for something. Okay, now there's some other quick and easy things you can do. If you always want, let's do this here. So edit the sketch again, and like I'll make it 2 inches, right? 2 inches goes all the way through the part. If I do 3 inches, it still goes all the way through the part. Now I've got a tube. All right, now to be fair, no, I'm not gonna go into that. Let's say though that I edit my first extrusion and I make this part 4 inches long now. Well, my cut was only 3 inches deep. Now I changed my part and made it longer. Well, now I don't have a tube, I'm back to having a cut, but I want a tube, I want it to go all the way through. So I can edit my extrusion here, and I can click here where it says extents, and it says where you have this box where you type in, there's also this box out here, it's the same thing. This is, I don't remember what this little widget is called. It's a widget, but they call it something special. But you can do everything you can do here, you can do in this window, it's either or. I typically use this guy, but for the class it's easier to see if I use this. So you can go up here where it says extents, the little drop down box. You can say it says distance. You can go to, and you can select another face, and it'll extrude up to that. The one that we want is all the way down at the bottom. It says all. Okay, you notice you can't set a distance anymore because it's going to go all the way through the part, no matter how long the part is. If I finish this sketch, right, I'm back to a tube. Right, if I change the part to be 12 inches long, right, I still have a tube. Okay, it's still going through the whole part. So in some cases, you want something to just go all the way through. And if it's going to go all the way through your part, you should use that extents all. Does that make sense? Okay, so you guys can create extrusions that add material. You can create extrusions that cut material to a certain depth. You can create extrusions that cut all the way through the part. And remember, you know, you can, any sketch that you can make, you can extrude either one of these ways. So you can do really complicated shapes if you want. You can also do equations. We go back to distance. We can also do equations here. I can do 3 plus 0.75 divided by 2, right? Should be 3.375. Okay, if you guys hit the M key, it's a measure tool, and you can click on two things, and it'll tell you how far apart they are. It's kind of useful. You just have to hit the M key. There's no button for it that I know of. I mean, there can be. I just don't know where it is. Okay, what are we ready for now? All right. Any questions on cutting with extrusions? Any questions on constraints or profiles or regions or anything? Yes.
How do you, so if the shape is purple, that means it's not fully constrained, right? Is there a way to tell which things still need to be constrained, or do you just have to look and figure it out?
You kind of look and figure out. You can click and drag on stuff and see what moves. That's often helpful. If you click on drag and stuff, if you click and drag on something that's not constrained, it'll move when you click and drag. So clicking and dragging and seeing, oh, it slides in this direction, but I can move it this way, that will help you figure it out. Also, if you look down in the bottom right-hand corner when you're in a sketch, you'll see here where it says fully constrained.
Okay.
There's
yeah.
words, if I delete a constraint, now it says I need one dimension because it's only, it has 1 degree of freedom. Basically, this tells you how many degrees of freedom your sketch has.
Okay.
So that can help you narrow it down as well. Occasionally, it'll glitch out and your sketch will be fully constrained, and it'll still say you need 1 dimension or something. It does that for really complicated sketches sometimes. So I wouldn't treat this as your like end all and be all. You know, be smart about it. It will screw up sometimes. Okay, so extrusions are great, right? I mean, you're going to spend the majority of your modeling time doing extrusions and similar things, right? But sometimes parts aren't, they don't have the same profile all the way through. You can't just look at it from the end and it'd be the same shape all the way through. Sometimes you want to do other shapes. So what we're going to talk about now is we're going to talk about the Revolve Tool. And the Revolve Tool does pretty much what you would expect it to do. It takes a shape and it revolves it around. Instead of stretching it this way, it stretches it in a circular fashion. Okay, and that's useful for making round parts, obviously. You don't have to extrude a full circle. You can extrude 90 degrees or whatever, any angle you want if for some reason you need to. So I'm going to create a new part. I'm going to create, I'm going to think of a weird shape. Let's see if you guys can constrain this. Okay. This is the origin point over here. I want you to make this shape. Now, pretend the lines are straight. Everything's perpendicular. I'm just bad at drawing. I want this line here to be in line with the origin. How do you think you would do that? Do a horizontal constraint. Also, coincidentally, just in this particular case, because this is a horizontal straight line, you could also do a coincident constraint, click the origin, and click the line. That would work as well. But a horizontal constraint will work between this corner and this corner. So I want you guys to make that sketch, make it any size you want, assign dimensions, but I want you guys to look in the bottom right-hand corner of your screen. It needs to be fully constrained. This one's going to be a little bit more difficult to fully constrain. You have to add a lot of dimensions and constraints to get it to lock it in place. And because this is a fairly complicated shape, there's a number of different ways that you can constrain it. When you're making a real part in the real world, you want to constrain it. You want to create the dimensions in the sketch that you care about in real life, right? If you're making a groove in a part, and you want the groove to be a certain width, dimension the groove to be the width you want it in Inventor. Don't dimension like the positions of the two sides of the groove or something, right? Dimension in Inventor the way that you want it dimensioned in real life in terms of the dimensions that you care about. And that'll just make it easier to go back and change the part later. Coulter, did you guys do attendance?
That way you want us to do it now.
I mean, the people that you know, go ahead and write down. If you don't know the names, just, yeah, go ahead and do as many as you can now, because I don't want to hold people up for too long. What?
That's done. You just have to, well, we don't.
Oh, you just, okay, all right. You're good then. All right, how you guys doing? You guys almost done? Who has a fully constrained sketch? Everybody, you got a fully constrained? I hear some mouse clicks there. I'll give you guys another minute or two to work. If any of you guys have if something weird's going on, you're trying to figure out how to solve it, just raise your hand and Coulter or Michael will show you how to fix it.
How do you tell if it's fully constrained?
Down here, it'll say, down here in the corner,
Oh.
does it say fully constrained? That is fully constrained. I've never had it say fully constrained when it wasn't fully constrained, but I have had it said it wasn't fully constrained when it was fully. But only really complicated. What? Does it say it's fully constrained down the corner? Well, you just start clicking and dragging and see what moves. If it moves, it's like constrained. You'll put dimension, you'll have to put horizontal constraints.
And this chair is breaking. Now, that doesn't look good.
It says I need dimension.
What does this button do?
Right, so you need to.
Configuration issues detected.
So
Ask me if I care.
together, but this doesn't have a position into the space. You gotta have to find a word. So you can do a horizontal constraint between this corner and that, and line it
I think I messed it up.
And you don't just need dimensions as well. If you look at my screen, try it, and dimensions.
So the towers. Honestly, why do they call it tilted towers? None of the towers are
Right, so
tilted.
you have the
Because what makes you get tilted?
This is constrained to itself. You have a different color scheme. So if you go to
It just says that I still have 2 dimensions needed and I don't know what to do.
It has to unload, when you do that, it has to unload the whole GUI and then reload the GUI, so it like freezes up for a second, but it should, yeah. So not everything will change, just a few things will change. Click sky, that's the color scheme I would. You can use whatever color scheme you want.
I have only just realized why.
It's just want you to understand that the reason that I don't use any of the others is because I like the purple, I like the dark colors and the lighter background. But if you like the color, you can delete the colors.
I want to delete you. Why can't I delete you?
You have the same problem I did if you want to show them what you did.
See this?
Can I kill this thing?
See this?
How?
See this?
You see this? I can't do anything to it.
What do you mean?
I don't know what I'm doing.
Austin, you're breaking your.
Okay, so, alright, so I don't want this to be attached to the origin.
I'm trying to delete this, but wait, I can't delete it. Let me delete you.
And then I want it to be, I want this bottom one.
This has been here since I started today, and I can't delete it. Wait, it's in constraint? How? I don't even know how to do a constraint. What are you? I hate this.
That'll take those 2 points and make some line.
Die. Let me kill you.
Go ahead and change it. Set it.
About 4:30 minus 10.
Dude, I'm just like confused on what I still do. What is this? Like I know this needs to be touching.
What is that? What are you?
Right, so you need to create dimensions.
Delete.
You guys have the same problem.
Yeah.
And then you need to work on that.
These mouses are too short.
On the dot. Oh, you accidentally deleted it. Okay. So if you want to delete your origin,
Can I put in an image?
center point. Click
Aww. Dude.
You're making good progress there, Tyson. Oh, okay.
Yeah, no, I couldn't figure out like how to do the horizontal thing because it wouldn't let me connect it. I was like, oh.
So you gotta click, when you're clicking 2 things, you gotta click 2 points. You can't click the line, you have to click the 2 corners.
Yeah, that would make a lot more sense.
Oh, you did what he did. Okay, so escape out. So you actually deleted your point in the middle.
You wanna get it back? So go over to origin, click the center point, and click project geometry. Yep. Now you can do what you were trying to do earlier. Austin, looks like you need to place a few more dimensions there. So you need to just look on my screen. You see how I have a bunch of dimensions up there? Just go ahead and do the same thing. Click one line, click the other. There. Yep. And then say how big you want it to be. And just go through and specify the size of each thing so it's locked in place. And Tyson, you want to help him do what you just did when he's done.
No.
Oh yeah,
It's when so if 2 dimensions you already have set as a certain thing, the program automatically detects that something else has to be that or like so let's say like you did dimensions for like certain things on like the side. So like the if you look at your sketch like the so if you did this, and this, well then this is a driven dimension because it already knows this. So basically,
I only have 2 more
if
left.
it already if the program already knows like what it has to be, then it'll make it.
Is it?
Your problem is.
Okay.
Okay, so to do it vertically, you just want to line this corner up and the origin horizontally.
How do you control this thing?
Okay, so that's okay. Vertical, and then you can just dimension from here to the center point to set how far apart it is.
Now you just need 1 more dimension. I don't know. I need 1 more too.
didn't get that last one. It says there's one left. Wait, can I move it though?
Oh, I know you're
Use a horizontal constraint.
No, I can't move it. I can move it. Whoa. To think, I learned how to do it in 3 seconds.
That line, that
I
corner
spent the
up
past
to the
hour
origin
just
horizontal.
drawing.
Now place a dimension between the origin and the line.
Oh, do I have? Is that what the last dimension is? Is that what the last dimension is?
So it's just a window select.
A.
So
okay,
let's
so fully constrained. That's okay. See, I'm used to SolidWorks when you're fully constrained.
Do I
It
have to do a
turns
vertical
dimension between the origin and that line. It's
wrong.
Yeah, more the corner. That's fine.
Just look at it.
Right, you're done. You've done it.
Nice.
I think.
Wait, I can't move it anymore. What the heck? Let me move thee.
It actually looks like you can just move it. So
What are you trying to do? I can't move it anymore. That's the point. That's why it's fully constrained. I thought constrained meant that you can move it.
You're so smart.
Hey, that's why I have a 3.2 GPA. I have a 3.2 GPA and I got 1 C.
That doesn't mean that you're not smart.
And my friends are like, you're not. I'm like, no.
Yeah, no.
Someone that I know, she had all A's and she got 1 B. She said it dropped her GPA from 4.2 to 3.3. And I was like, there's no possible way that getting 1 B would drop your grade point
If
average
you have
that
all
much.
A's,
Yeah.
it might drop it to like a 3.9, 3.8, maybe.
I had a 3.8 first semester and I had 2 A's and all the rest were just B's. Which Spanish, I got a 79.7 and she wouldn't round it up.
My first quarter Spanish, I got, it was like an 82%.
I had an A in that class
My second quarter Spanish,
and then I missed Worlds. I missed for Worlds and then I had a D originally and I was like,
my second quarter Spanish, she told us that we had this project, and so we had to pick a Spanish-speaking country. She kept changing all this stuff. So she didn't give us the rubric until the day before it was due. And then she kept changing stuff on the rubric that day before it was due. And then everybody already had their projects done. So I just went home and I was like, you know what? I'm gonna
Alright, guys,
fail this
we're gonna-
project anyway. So
We're gonna move on. I
didn't
think all of you pretty much have the shape that I have on my screen. All right. So in order to revolve something, we have to have a center line. We have to have a line that acts as the axis that we revolve the thing around. Okay. So now that line can be part of a profile. Okay. So if I had a box, I could use the left side of the box, revolve it, and I would get a cylinder. But in this case, we have a little more complicated part. I want there to be a hole through the center of the part. All right, so I don't want to revolve it around its one side. I want to revolve it offset in the sketch. That's why I was so adamant about you guys having this gap between the origin and your part. So we need a line that will act as the axis of rotation in our sketch. Now the length of this line is not important. I'm just going to make it 1 inch long. But I'm going to go up here, I'm going to create a line, I'm going to click on the origin, I'm going to go straight up, I'm just going to make it 1 inch long, which you can type in the box while you're creating the line, then just hit enter. Or you can create the line and dimension it afterwards, up to you. Okay? Everybody got a center line? Okay, so finish your sketch. And to revolve it, click the surprise, surprise, revolve button. Where? You have to finish the sketch.
oh.
See what happens when you miss a week, Austin?
I had driving school. No, I didn't. Long day.
Wow, you
It's just-
liar.
I had a performance.
Alright, so similar to a sketch, so in an extrusion, you just have to pick your regions, say how long you want it to be, and you're done. Okay? For a revolve, you need to pick your regions, specify the axis, and then say how many degrees you want it to revolve. Now by default, in this box here, it'll revolve full, it'll revolve 360 degrees, which in most cases is what you want. It's rare that you want to only revolve part of a way. But so you can see over here, there's a profile button, right? That's for selecting your region. There's an axis button. So go ahead and click your region, okay? And then select the axis button, and then click your line. And all of a sudden, bam, it will revolve part. Then you can click the OK button. And it will revolve part.
What did you do?
Profile. This. What the heck?
Why did Michael, you want to people that are hopelessly lost? Why did Michael? What?
Dude, yours can fit mine.
Dude, what did you do?
I don't know.
I'm so confused.
I clicked profile. I clicked it. And then
He used the top. He used the top as his axis.
I did. I'm so confused right now. I'm revolve. Profile.
Let me,
Oh
okay.
yeah, I clicked axis.
Let me do
first.
something here real quick, guys. This is going to be important for when you guys are working at home. Okay, let's say I have a profile and I extruded it, but I want to revolve it instead or something. Like I don't want to delete my sketch, right? Because if I just go over here to Revolution 1 and right click, delete, click OK, it just deletes the whole thing. My sketch is gone, my revolution is gone. That's not what I want. I want to delete the revolution, but I want to keep the sketch. Okay? You'll do this a lot. So if you right click on Revolution 1 and click delete, just like I did before, and you see this box that pops up, it says additionally delete consume sketches and features. Uncheck that box, then click OK, and you get your sketch back, but you don't have but you deleted your revolution. You'll do that a lot. So you just gotta uncheck when you delete, you just gotta uncheck that box before you click OK, and then you'll be good. Okay, so Micah, here's what you did.
Wait, what do I do now?
Austin, you too. You click revolve, you click your profile, and then when you click your axis, you picked one of these side lines.
Yeah.
Right, like Micah, I think you did this one.
Okay.
You should click this line for your axis. Select your region, click axis,
Do you like
and then click the line. That'll give you
Where did it go?
One that I made.
right, the little line that comes off the origin.
Is there a normal to button? Like on software?
For what?
Like, okay, so.
Oh, you want to view your sketch?
No, I'm saying, so like, you can go do something like that where it like sets it.
That's what that is. Now you'll have to go over here to the planes to click which plane you want because you don't have any surfaces.
I haven't listened to Post
Oh,
Malone.
thank you, Ryan.
Who's your favorite singer?
Singer.
Oh, you like dubs, right?
Singer is a very general term.
Who's your favorite rapper? I like Post Malone.
Yeah, you see, you have a hole in the
You just put your line in the spot.
I like No Limits by G.
So you select
Okay.
This way.
Look up reverse and you need to not
No.
So
I'm going home and play some.
Why are you drawing on that lady's face?
Because you're stupid.
Do I need to hit OK?
okay.
So you want to
You click. I want to give this.
Wow, he has a blue mustache.
So basically split open
so okay. That happens you'll notice.
No, he's Dumbo.
You're a Dumbo.
Notice this is very. That means that on one of these.
Wait, I got an idea. Wait.
Figure eight. You should be proud of me. I can do relaxes and decayances. Wow, look how bald this is. Dude, my brother is 21 and he's balding terribly.
He's got a noose.
No, here. You want put it back in the I don't know how to do it.
So,
Put it back in the
I gotta wonder what's in the
Okay,
stuff.
let me
Dude, we can play Hangman.
This dimension.
No!
See, that's what that was gonna be.
Oh my god. Alright, everybody got that shape? Anybody else need help?
No!
What?
I got a weird
Coulter.
shape. I don't know why.
Back row, or Michael, I don't care. Right here. They need some help.
Specifically need a right.
I've got both ways.
Yeah, boy.
Okay, guys, that's it. That's our class. It's 8 o'clock. That's everything that I had to go through tonight. So practice this some more at home. There's little nuances that you'll just have to explore yourself because we don't have enough time to go into all the details here. A lot of tutorials on YouTube. Inventor has some tutorials built in. Inventor has really good tool tips. So if you just hover over stuff and you want to know what it does, it'll tell you. So, culture. You want to? Who are you missing? You want to take attendance before everybody leaves?
Yeah.
What type do I say?
What do you do?
Hey Ryan,
Hey, Ryan.
are there like pre-made parts or like pre-made models for like
I'm gonna kick
motors and stuff that you can download?
How do you say?
And are there any like specific sites that
If you go to Vex,
Convert to sheet metal. Sure, I'll do that.
McMaster Car also has models. They're not. The thing is, they're not inventor models. They're what are called step files, which is kind of a universal 3D CAD thing. So you're not gonna like when you import it, you're just gonna get kind of a lump, right? It's gonna look right, but you're not gonna have like extrude and revolve. You're not gonna have
Oh,
those features.
yeah.
I'm actually in 2 weeks. I'm going to talk about how to do that, so you can try to figure it out yourself. If not,
And what are we doing next week? Because I have a Python class that
we're going to go over assembly.
Oh, okay, that's
Oh, assembly line.
no, wrong.
What's this? I'm gonna click that button.
Assemblies are much fun many while.
Let's say changes, sure. Alright.
Y'all remember your flash drives to save all your beautiful parts?
I have one, but I didn't use it because this is it.